any applications where materials are subjected to conditions that might cause damage, and that damage can compromise the material's ability to function in that particular application, is a potential application for self-healing technology, right? We can think about applications that are maybe adjacent to coating. So think about things like sealants and adhesives and composites, for example.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And also, we have a free MSE Company Database categorized by industry sector, location, as well as internship and full-time titles. So if you're interested in that, you can find the link in the description below. And now, let's get on to the episode.
Hello, everyone. We have a fantastic guest for today's episode in Dr. Gerald Wilson, the president and CEO of Autonomic Materials, an industry leader in self-healing technologies for coatings, sealants, adhesives, and composites. Gerald led the development of the coatings industry's first set of additives designed to impart self-healing functionality into industrial water-borne, solvent-borne, and powder coatings. From his research at UIUC to his work at Autonomic Materials, he has developed an extensive knowledge base in self-healing polymers. So we're super excited to have him on the show today. Thank you so much for joining us today, Gerald.
Absolutely. It's my pleasure. It's good to be with you guys.
So we want to just start off with the basics, the ground level. So self-healing materials at the surface level kind of seems self-explanatory, but there's a whole intricate mechanism that comes into play. So I was just wondering if you could kind of talk us through how they work and maybe give us an example of self-healing mechanisms, because I feel like there's differences, right? There's different mechanisms.
Yeah, sure, absolutely. So I think a good way to think about what self-healing materials are is to think about imparting functionality into materials that allow them to recover their most important properties after damage. Okay, so that's sort of the main part of the definition, is what happens after damage. So from that standpoint, there's been a lot of research into designing self-healing functionalities into various types of materials. I think one good example would be, what sort of underpins a lot of the work that we do at Autonomic Materials, where we use a process called microencapsulation to build a polymer shell around a liquid material. And that liquid material we refer to as a healing agent, right? So that microencapsulated healing agent is then embedded into a material, so that when the material is damaged, that microcapsule or set of microcapsules are broken, that healing agent is released into the site of damage, where it helps the material recover its original properties.
So how exactly, what about the healing agent allows it to kind of repair the material as a whole?
Sure. First of all, the microencapsulation process allows us to build a shell wall that is really well bonded to the material. We think of that as the matrix, right? So if you think about a coating, for example, if that microcapsule is well bonded to the rest of the coating, when that coating is mechanically damaged, that damage transfers from the material matrix to the microcapsule shell wall, which causes this to rupture. And then what we've done is design a healing agent that is basically a blend of polymer precursors, corrosion inhibitors, adhesion promoters, that when it's released into the site of damage and it polymerizes, you essentially now have a material that is a lot like a coating. It's got a polymer binder, it's well bonded to the underlying substrate, and it has a corrosion inhibitor in it that helps mitigate corrosion. So it's like replacing coating where it's lost, is probably a high-level way of thinking about it.
By replacing the coating, and you're talking about all these additives, is it the same additives that would be already on the surface, or are you adding new materials to change the properties as wear occurs?
Essentially, what we're doing is trying to help the material recover as much of its original properties as possible. So if we're talking about a coating, those are barrier properties, right, for protecting the underlying substrate, its corrosion resistance type properties. So we're trying to design a healing agent that is pretty similar to the rest of the coating.
And so you mentioned a polymerization process. So I was just wondering, like, there's like a termination step with polymerization, right? And I was wondering if that's something that is a challenge in terms of like finding the right place to terminate that process, or am I kind of not thinking about the right thing, or when it comes to like properly repairing and providing enough material to kind of restore those properties?
Yeah, sure. So there's several different types of polymer chemistries and resulting polymerization mechanisms. In this case, we design our healing agents to take advantage of thermosetting resin systems that will cross-link at the site of damage, right? And so in those instances, they'll cross-link. That polymerization will proceed to higher levels of conversion until you reach a point where conversion is no longer possible, not to get too technical, but is no longer possible below the glass transition temperature, right? And so it effectively terminates at that point in time.
So you've also followed a unique path as you've pursued both your PhD and your MBA at UIUC to gain a deeper understanding of self-healing polymers, but also the business side of things. What drove you to this decision to pursue a technical and business degree? And in what situations would you recommend to our listeners that they should do the same?
Yeah, I think I was always just sort of fascinated with both sides of thinking about innovation and product development. Going back to my undergraduate work before going to the University of Illinois and getting a PhD in material science and engineering, I was a chemistry major as an undergraduate. And even back then, I, for a while contemplated a double major in economics, right? I was always sort of fascinated by how you can use technology, science to create value, and was passionate about learning as much as I could, about the combination of those things. So I think my curiosity sort of led me in the direction of trying to understand how I could build a career at that interface between technology or product development and business. And so I followed my curiosity down that path, and that sort of led me to studying both material science and business. And I would say, to the extent people find themselves sort of drawn to questions that kind of straddle the interface between product development and business, I mean, it's a pretty natural interface, right? In order to bring a new product to market, you sort of have to understand, how you're creating value with it. So I think if you're drawn to answering questions at that interface, then I would say studying in both areas is likely to help.
Yeah. And I would also say that you don't necessarily have to feel like you want to be like start your own business and follow this like entrepreneurial path right out of the gate in order to also get a business degree or take business classes as well. Like from what I've seen, it's a long-term play a little bit, but if you want to go down like a managerial path, it's important to have kind of that systems level view of things and kind of understand the business impacts and the business risks in addition to the R&D side of things. So would you kind of agree with that statement too? Like, or would you say that
I would to a certain extent, but I would also say that getting a business degree is not essential for getting that systems level view, right? So I wouldn't want people walking away with the idea that you need an MBA in order to chart a career path that takes you through management over the course of your career. I think these are things that you can learn on your own in a lot of different ways. A lot of them you can learn as your career develops as part of an organization. I think for me, my level of interest in both areas and my curiosity and passion for how I could leverage that interface led me, in that direction of wanting to get a little bit deeper. But I think it really is a function of what people ultimately want to do with their careers. But all those options are ones that could lead to having that systems level management type contribution over the course of your career.
Yeah, absolutely. I was also wondering, what were the main advantages you found from, getting your MBA degree, as opposed to, like, I feel with just getting the hands-on experience of running a company, you also learn a lot about the business side naturally. So what are the main advantages of getting your MBA in addition to that technical degree?
It sort of complemented what I was doing every day in the business, right? So rather than, working on something very specific, trying to figure out, for example, how to put the right marketing strategy together for a business, I was getting a broader view while getting my MBA, right? Getting introduced to various frameworks that could be leveraged in figuring out how to think about a problem like that. So I think it just complemented, what I was learning every day, trying to get our business off the ground, with what I was getting while pursuing my MBA. And the other direction was also true. I found that because I could take what I was learning in the classroom and implement it right away, which most people don't have that opportunity to implement the broadest scope of what you might get exposed to in an MBA program right away. And I was able to do that. And so I think I was able to come back to our discussions in our courses with real life concrete examples of how some of these principles could be deployed. And it helped me, I think, get even more out of that program.
Yeah, absolutely. I guess this is a question for David then. Like, how did your technology and management minor help with that sort of thing and your kind of passion for the business side of things?
Yeah. So my minor was basically just a business minor for engineers. And I think that it just exposed me to a lot of concepts. And like Gerald would say, you just kind of get a nice breadth of things to understand when you get into the workforce, just like kind of what's going on. Of course, it's nowhere near as in-depth as the MBA. So it was really just to get me familiar and understand the basics in a way that made it very easy to transition when I actually did get into a position where it needed it, to take what I knew and quickly learn and build upon it, but already have a strong foundation to at least know what's going on and what steps forward would be. So I think it was just very good to get an overall view and basically set myself up to grow upon that if that's the road I wanted to go.
Yeah.
So I guess the frameworks are key there for both that business minor and the MBA. But now we can kind of take it back to self-healing materials, which is the focus of this episode.
Sure.
There seems to be a lot of potential for innovation in this space. And I know we'll talk about kind of the coating industry in more detail soon, but to start out, what other applications can self-healing materials make an impact in?
Okay, so if we just go back to the way I define self-healing materials, which is the ability for a material system to recover its most critical functionality after damage, right? So then if you think about it from that perspective, then any applications where materials are subjected to conditions that might cause damage, and that damage can compromise the material's ability to function in that particular application, is a potential application for self-healing technology, right? And that's a very broad range of potential applications. I think that, just to keep it, fairly narrow for the purposes of this conversation, we can think about applications that are maybe adjacent to coating. So think about things like sealants and adhesives and composites, for example. In a lot of those applications, you have materials being used in very critical functions. So if you're joining two parts, for example, say in an automotive application, you're using a structural adhesive. That's becoming more and more common as lightweighting becomes an important feature of designing the next generation of vehicles. David would be very, very familiar with this idea. When you do have adhesives, for example, joining two parts, let's say dissimilar materials, for example, that creates a lot of stresses in that adhesive joint, and you begin to get cracks that form in the adhesive joint, and that those cracks will propagate over time and lead to some kind of failure. And what you want to avoid is for that failure to be catastrophic. And so designing in self-healing functionality, even using microcapsule-based technologies like we have, will arrest that crack early on and prevent its propagation, and therefore slow down the rate at which it might propagate to the point where you might have some sort of catastrophic failure. So that's one sort of adjacent example of potential applications, but you can see how that could be transitioned into sealants, into composites, and other material systems like that.
So for all these technologies, it sounds like the major way of releasing the self-healing is through some sort of impact with like the fracture. And then the fracture is like another way of impact, which is just like stress concentration at the tip of a crack.
That's right.
What other types of mechanisms could be used for activating self-healing materials?
Yeah, there are a few other ways you could approach it, right? So, for most of the work that we do, and I would say the work that is most advanced, even in academia, you have to somehow find a way to compartmentalize a healing agent within the material system, right? So we use microcapsules. Some of the work that's gone on at the University of Illinois, the research group that I was a member of, they've sort of gone on and taken the approach of designing in microvascular systems, for example, that are basically vascularized systems that contain a healing agent that allow that healing agent to be more present throughout the entire material. So once you take that step to compartmentalize, then you can look at a number of different methods for facilitating release of the healing agent from those compartments. Okay, so we use stress concentration as you described it, David. But you can envision using heat, for example, if you're in an application where use conditions are such that ambient temperature is relatively high. You can envision chemical changes, so for example, pH changes that cause the rupture of microcapsules or trigger release of healing agents from a vascularized structure, for example. So the reality is that it boils down to design, but you can design a fairly broad range of external triggers to initiate a healing response.
And to what extent, with current technologies, like what scale can like a crack be repaired in a material? Because we did a capstone project where we were just like learning the product development process.
Mm-hmm.
So we were just kind of like making up a technology, and we chose self-healing body armor. David's laughing at this, but because he heard it from me 1,000 times. But I guess that's a pretty big impact, right? Like a bullet makes a pretty big impact, and then I guess it would have to repair itself on a pretty quick time scale. So I just wanted to hear, like, realistically, where are we at with that technology in terms of like the maximum scale one can repair itself at?
Yeah, that's a good question, because there's a lot going on in academia, right? So, a lot of that is still pretty far away, I would say, from being commercial. I wouldn't say far away. That's probably not the right way to describe it, but there's still a lot of work to be done in bringing some of those technologies to market. And I don't know on the large end of things that I want to put a number on it, but I would say certainly visible damage, can be repaired with technologies that are sort of at our at the level of what we're working on, what we deploy in coding systems. But I think that, some of the academic work that's going on right now has that damage that's being repaired, becoming, fairly large, on the order of even a few centimeters, based on a number of really interesting polymer chemistries that are being developed right now.
In a previous call, you explained a 2x2 matrix that explained the self-healing coating industry really well. Could you talk us through this in more detail and what applications may look like in each quadrant of this matrix?
Sure, I'm happy to do that. So that was sort of my way of trying to segment, the technologies that are out there, whether they've been commercialized or still at the academic stage. And think about where they could actually be used, right? So the technologies that, I think can be broadly segmented into those that are what I would call truly autonomic or truly self-healing. So those are the ones that don't require any sort of external intervention to drive the healing response, right? So the material is being used in a specific application, damage occurs, a healing response is triggered, and that's an autonomic response, truly autonomic. And then you have those that require some kind of external intervention, right? So you can visibly see that the material, let's say a coating, for example, has been scratched, and you can apply UV radiation or heat or something like that to alleviate the appearance of that scratch. That I think of as non-autonomic. Okay, so if you think about a 2x2 matrix where you have non-autonomic on sort of the x-axis, the lower left side of that quadrant, and then autonomic on the right, and then you start mapping those to applications as to whether they're more aesthetic. So think about, the appearance of your cell phone, for example, if you scratch it, or your vehicle, right? That's I see that as more of an aesthetic response. So think about that aesthetic response at the lower left end of that quadrant as well. And then on the top left side of that quadrant, think about it as protective, mitigating against corrosion, right? More of a heavy duty type protection. So you can have technologies then that are both autonomic and aimed at a protective kind of application. That's what we focus on. So the chemistries that we develop at Autonomic Materials would fit in that top right quadrant, right? But there are also technologies that are, that have been developed in academia, for example, that could be envisioned for use in a protective application, but require that external intervention, right? So those would be in that top left quadrant. And then the bottom left quadrant, where the technologies are aesthetic and non-autonomic, a lot of those are what get routinely reported in the media. If you do a search on self-healing and you start finding technologies that have been evaluated in automotive clear coats or on electronic devices, for example, most of those require some kind of heat. And so they will fall in that quadrant. And then the holy grail, I think, as far as aesthetic applications go, will be those that are in that bottom right quadrant, right? That are both autonomic and aesthetic. From a material science or polymer chemistry standpoint, that is extremely difficult to accomplish. But that, is, assuming the value is there, because people are, upgrading their phones as often as twice a year in some instances now. So you may decide that the value, other than, maybe the novelty of it, and from a product developer standpoint, the differentiation there, I could see in an automotive application, for example, that actually having some significant value. And that's certainly an area of really interesting research for the future.
Interesting. So just to recap, so the axes are like non-autonomic to autonomic, and then also aesthetic to protective. Is that correct?
That's correct. Yep.
Okay.
That's correct.
Got it. Cool. All right. So then taking all of that into consideration, we read about one of your technologies. It's called AmpUp-RB, I believe, which is a self-healing protective solution for rebar and structural metals embedded in concrete. So I remember freshman year, David and I, we read about self-healing concrete in like our first year of college in a book called Stuff Matters. And it talked about how like bacteria was embedded in concrete to make limestone from like other materials and therefore like fill those cracks. So I guess like to the extent you're allowed to talk about it, considering the proprietary technology, can you just walk us through like the general material selection involved and kind of the mechanism that allows for not just an aesthetic solution, but the corrosion protection as well?
Sure. First of all, I'm just really impressed with how much exposure you guys have had to self-healing materials in general, going back to your undergraduate work. So AmpUp-RB was really a response to some really difficult things that are sort of happening in the world of construction, right? So I don't know if you guys, saw in the news, a few months back, the condo collapse, Surfside condo collapse in the Miami area. There was recently another 5-story building that was evacuated because it was deemed unsafe. The reality is that in architectural type applications, you need steel reinforcement to give these structures the structural integrity that you need. The challenge is that concrete is a porous material and steel corrodes, right? So if you have these structures that have steel reinforcement in them and they exist in really corrosive environments, you're going to get those chlorides penetrating those pores and initiating corrosion. And when you begin to have corrosion on the rebar, then you essentially begin to build up corrosion product between the rebar and the concrete, right? And that creates stresses that ultimately lead to cracks in the concrete, creates more avenues for more chlorides to enter. And before long, you have a rebar or steel reinforcement that is really corroding. And of course, as it corrodes, its ability to provide structural integrity gets compromised. AmpUp-RB was a response to that, right? We knew that we had developed self-healing coatings that are showing just industry leading and just unprecedented performance in applications in other extremely corrosive applications, like in water parks, for example. And so we started thinking about how we could give engineers and contractors a solution as they are repairing those assets where you have reinforcement that is significantly corroded, give them a solution that would perform much better, right? So what we essentially developed was a coating that has our self-healing technology in it. And so that when you begin to, so that would be applied on the rebar during concrete repair. It can also be used on the rebar prior to installation in a new build, so that when you begin to have the stresses in the material that causes the protective coating on the rebar to fail, you would get rupture of our healing agents that will basically be released and keep that coating bonded to the rebar, preventing the ingress of chlorides that would ultimately cause corrosion. But the challenge with deploying new technology like that is there's a trade-off that engineers often have to confront in protecting rebar, which is that generally speaking, there are products out there that protect the rebar really well, or reasonably well, I should say, but have really poor adhesion to the concrete, which is absolutely essential, right? For being able to transfer that load from the concrete to the rebar, you have to have really good adhesion between the rebar and the concrete. So if your adhesion of your concrete materials to the rebar is poor, then it's not going to function as well as a reinforcement, right? Now, on the other side of that trade-off, is optimizing for adhesion to the concrete. Well, when you do that, you use cementitious coating materials, for example, that will facilitate good bonding with the concrete. But those are going to be porous, and they're going to just have poor barrier properties and just be incapable of adequately protecting the rebar. That is the equation that we've solved with that product, the AmpUp RB, is that it's got the self-healing functionality, it's got just outstanding corrosion protection, but we also designed it to have really good bonding. Actually, when you compare it to other rebar coatings, relative to unprotected rebar, it's maintaining 99.2% of the adhesion to concrete. Whereas, some of the other incumbents are hard pressed to get to 90%, right? So leveraging our technology platform and some really smart formulation, we were able to develop something that was truly groundbreaking and is already, making an impact in those areas where rebar protection is essential.
Wow. So I guess my follow-up question there is, are there like processing challenges when it comes to having microcapsules and healing agents? Like, what does that production process look like?
It's a good question. When you're starting a business commercializing technology that was originally developed in academia, you make a lot of assumptions about what's going to be hard and what's going to be easy. The scale up of microcapsules is something that I spent a number of years trying to solve. It's not as easy as it sounds, given the target application, right? So microencapsulation as a technology has been around for a while. If you are familiar with, carbonless paper technologies, I mean, younger folks in general, most of us don't have as much experience writing checks, for example, but that was one of the biggest applications for it, was that you had microencapsulated ink that was coated on the paper. So when you wrote on one side of it, it would rupture these capsules and the ink would be released and it would make an imprint on the other side of the paper, right? So for the longest time, that's what microencapsulation was used for. And we're using it to microencapsulate a healing agent. Now, scaling up a healing agent blend, that's not hard. Microencapsulating a healing agent, also not very difficult, but doing it at scale in a way that will mitigate, the agglomeration of these particles, for example, is a lot more difficult than it sounds. And then we also needed to take the step of functionalizing the shell walls of these capsules to facilitate really easy dispersion in the target coating formulations, right? So we developed a lot of trade secrets, a lot of new processes, some new intellectual property, just around scaling the technology up and optimizing the ability to disperse these capsules in target coating formulations. Yeah, it's not unusual for people to think, well, you're making a microcapsule and putting it in a coating. How hard can that be, right? But it's certainly, fairly complicated, and we spent a lot of time working on trying to figure out, the way to do that in a way that's scalable.
Mm-hmm. I think one major key that we haven't talked about yet with self-healing polymers is the sustainability function of it.
Mm-hmm.
And it's an extremely important aspect to your company as well, as it can help extend the lifetime of products and ensure that they last as long as possible. How does Autonomic Materials plan to innovate to even higher levels of sustainability in the future? And what steps are you taking to achieve these goals?
Yeah. Well, so if we just sort of want to go back a bit to just, at a very high level, just talk about what inspired the research on self-healing materials. The professors that I worked with at the University of Illinois, Scott White, Jeff Moore, Nancy Sotos, Paul Braun, who pioneered this field of materials science, were inspired by the idea that polymeric materials are generally manufactured from feedstocks that come from unsustainable sources, right? And so when you look at that fact, and then you look at what really continues to be a very inefficient recycling efforts around polymeric materials, then it sort of made sense, right? The idea that regardless of the application, if we could design in self-healing functionalities, that these polymers will last longer in those target applications. Now, when you think about what that means in the context of designing protective coatings, right, which is what we do. If we sort of just want to go back to thinking about the inspiration for self-healing materials, going back to the faculty members that I collaborated with as a student, Scott White, Nancy Sotos, Jeff Moore, Paul Braun, they were all very interested in leveraging this self-healing functionality to lengthen the lifetime of materials in their target application. And that makes sense from a sustainability standpoint, because if we're not using polymeric materials from renewable sources, then let's use less of these feedstocks by keeping these materials in service for a longer period of time. Now, when you think about how that applies in protective coatings, the sustainability impact, I think, becomes magnified, because not only can you design coating systems that last longer, and therefore you're using less of the polymer feedstocks that make those coatings and all the other components that go into them, but you're also protecting the steel for a longer period of time, which means using less steel. Now we're taking that one step further as Autonomic Materials by leveraging the self-healing functionality to design lower VOC, volatile organic compounds, products that release less toxic chemicals into the environment, right? So, that's another trade-off that exists in the coatings industry. Typically, if you want high performance asset protection, you're getting that from solvent-borne coating systems that release VOCs into the environment. So that's another trade-off we're eliminating, because, we're designing low VOC coating systems and enabling high performance corrosion protection using our technology. Now, when you think about designing a self-healing materials system, there are basically three domains where you're using materials. You've got the healing agent, that is probably best to start the other way. You've got the actual material itself. So it's a coating, it's an adhesive, it's a polymerized resin. Then you have the healing agent blend that you're trying to use to impart the self-healing functionality into it, right? So that's the second sort of domain of material usage. And then you have the material that you're using to compartmentalize the healing agent, right? So in all of those domains currently, we do our best to use components that are low VOC, have minimal impact on the environment, but generally speaking, it's still really difficult to get away from using resin systems that come from renewable sources. So that's, I see as sort of the next step for us, a next step towards having a design system, a product development approach that is truly circular, is actually using resins, other raw materials that come from renewable sources.
Fascinating. So you mentioned the issue that arises with more VOCs, and that's a challenge that seems to persist in this self-healing polymer space. So what do you think MSEs can do to kind of help address these challenges and continue to innovate and create a more sustainable future, while ensuring that this equipment or whatever these polymers are protecting still has an extended lifetime?
Yeah, I think the focus really needs to be on the raw material side. There is some research going on to design resin systems from renewable sources, from plant-based materials and things like that, but likely not enough. right? And so I see that as, one area of research that we could all benefit from seeing grow tremendously. But I also think that, at least at an academic level, beginning to see, some of the research on smart coding, self-healing, begin to leverage some of the material systems that are coming from those renewable sources to at least begin to demonstrate, how you can compartmentalize those types of materials, how you can build shell walls, for example, in a micro capsule based system, or how you can use them to make vascular structures within material systems. I see that as sort of the next area of potentially really exciting research.
So I guess we discussed quite a few like applications and the basics of it. David, did you have anything else you wanted to add? Any last minute questions?
Yeah, I just wanted to ask that you talked a lot about scaling up with the materials, but as you said, things sounded a lot easier before you actually do it. With the introduction of potentially new sources of materials, do you foresee, will we have to change the way we try to encapsulate it, or is that even potentially an improvement that we can change the way we encapsulate these materials?
Potentially, it's hard to say until you get in there and start working on this kind of stuff. But to me, that's where all the opportunity for innovation and new intellectual property and just really new groundbreaking research lies. My sense is that it's going to take some new polymer chemistry to work with those types of raw materials, to design new capsules based on shell walls that come, that are renewable, recyclable, circular, and yeah, to me, there's a lot of exciting work that can happen there. But there's no question that we're talking pretty early stage R&D and trying to solve those kinds of problems. Going from that level to something that is ready for commercial introduction, there's going to be a lot of really, really cool problems to solve along the way.
And I was just wondering, do you coordinate or collaborate with the academic side of things and research at universities when it comes to innovating in the space?
Yeah, we have, like I mentioned, our technology was originally developed at the University of Illinois. That's where I did my graduate work, and we maintain just really good collaborations with that research group. In fact, we're currently working with them and partners at Carnegie Mellon University on a really, really neat project around designing basically the next generation of rehabilitation materials, rehabilitation systems for legacy natural gas pipes. And it's just, just really, really neat material science, robotics, just a really cool project, very multidisciplinary, bringing experts from a number of different backgrounds to solve a really challenging problem. So that's, I would say our deepest level of collaboration goes with the University of Illinois. But we've cultivated a brand as leaders in the self-healing space. So what that has bought us as well is, researchers working in this space, wanting our feedback on whether or not something that they're working on has commercial potential, and initiating discussions around potential collaborations with us. So that's nice as well. The opportunity is always there for those kinds of collaborations.
Cool. So we definitely discussed the fundamentals of self-healing materials in great detail, and we really appreciate you sharing your experiences and your insights with us. So
absolutely.
To kind of conclude this episode, we would love for you to share your final piece of advice that you would give maybe your 20-year-old self who was in the early stages of his chemistry / MSE career.
Yeah, with the benefit of hindsight, I would say that, my hunch, my intuition, as I was, starting my career and studying, chemistry and material science was that this was a great field to be in because it's so multidisciplinary, right? And I really think, being, shall we say, just a few years more into my career than you guys might be at this stage, that value is really created at the interface between disciplines, right? I mean, you really need people from multiple backgrounds to solve most problems that are worth spending time on. And so, if I was talking to my 20-year-old self, I would say, yeah, definitely go ahead and study material science. It's going to give you the ability to communicate and collaborate with a very, very diverse group of professionals. That's one of the biggest things that I've been able to get from it. And that's not to say that if you were doing something that is less traditionally multidisciplinary, like chemistry or physics or something like that, you don't get that. But the discipline of material science is inherently multidisciplinary. And there's just something that comes with that I think is difficult to get elsewhere. But I would say, I would, talking to myself at 20, I would say push that even further, right? Do a broader scope of internships, right? Do undergraduate research that is broader, collaborate with people in political science on the policy aspects of sustainability, for example. Explore more widely. So coming from me with my interest in multiple disciplines, from material science to business, that's probably not surprising, but that's what I would say is, rather than be very, very focused, take the material science background and explore all the different directions you could take it early on in your career. And you ultimately find what interface between disciplines you can most uniquely add value in.
It's really interesting that you note that. We kind of had similar advice just like a couple episodes ago, but that further emphasizes the point of kind of having that interdisciplinary background, and that there's a lot of innovation on those like interfaces between different disciplines. And I'm seeing it right now with like one of my projects at Boston Scientific too. Like my polymers internship from a few years ago is really coming in play, and kind of, I definitely agree. And I just wanted to reiterate like our appreciation for you joining our show today. I learned a lot.
Absolutely. This was a lot of fun. It was great, talking shop with you guys for a bit.
Yeah, absolutely.
As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.